Okay, everybody, welcome back from spring break. Here we are with geometrical optics. I think you'll find this chapter to be a bit refreshing. You'll actually be able to, no pun intended, see some of the effects of these. And the mathematical representation is relatively simple. We're mostly going to be dealing with fractions. An important part for working through geometrical optics is for you to have a straight edge. A ruler's great, but you definitely need a straight edge. If you've got a protractor, that'll make things even easier for you. You won't have to guess when you're dealing with angles. But it does say geometrical, so at least have a straight edge. And I recommend having the sharpest pencil or narrowest pen as you're trying to draw some of these types of diagrams. So we'll just jump in here and talk about optics. Optics is simply the study of light. So if we look at least back several centuries, there were people studying optics. You have the invention of eyeglasses around 1300 AD, and then microscopes and telescopes around AD 1600. When we go to look at applications nearer to the end of the chapter, we'll notice that many things that we're going to apply optics to, we're going to have to know about the lenses and the mirrors, and the better they are and the better they bring things into focus. When we're looking, remember that light is an electromagnetic wave. So we talked about that before the break. And so it does have wave properties. And so we'll need to account for those. We'll talk a little bit about that in this chapter, but most of the wave properties we're going to see manifest themselves in physical optics, which is chapter 25. So geometrical optics, what are we talking about? It's when light travels in straight paths, and we can pretty much discount the wave interference patterns when we're looking at geometric optics. So we're describing cases where the wavelength of the light is much smaller than the size of the object in the light's path. So we know the wavelength is very small, 400 to 700 nanometers for visible light. And so any object that you can easily see is going to be under the rules of geometric optics. And so we're going to concentrate on lenses and on mirrors. A few things to think about. Instead of just thinking about waves, we're going to think more about the direction that the light goes. And so we're going to begin to talk about rays. And the ray for light indicates the direction of the path. And so what is the direction of propagation for the light wave? We would say essentially it's the direction piece of the velocity vector from the electromagnetic wave. So if you're looking at this diagram from your book, the wave passes through this large opening and follows a straight line as it passes through. So you get an opening, and then over on the wall or whatever screen over here, there are dark places. And then there are light places where the light hits. Right? In B, the opening is much smaller. So when I'm looking at this opening, it's smaller, and I start getting some interference patterns. So notice this light, dark pattern. That's what we're going to look at in the next chapter. So chapter 25, we're going to be thinking about those interference pieces. So what is that ray really that we're talking about? Well, if we're thinking about the wave fronts, or really looking at the wave, so typically, and this is the way your book does it also, kind of thinks about here's a crest, and then that crest moves here, and then here. So the wave speed is the speed for which the wave fronts or crests are traveling. If it's moving out spherically, then notice that these, as we've seen before, are going to spread out, and so the light is going to be less intense as we get further and further away from the source. And so when we're looking at spherical waves, like in part C here, now we've got this opening, and we've essentially selected out some plane waves from a spherical source. A light bulb is going to give us spherical waves as it moves out. But if we open up a small opening, the waves that go through it are pretty much going to be planar type waves. So, to recap, light rays are going to travel in straight lines until they run into something. When they encounter a boundary between two media, then we've got a couple of options. One is they can return right back. That's what we call reflection. Or sometimes the ray will pass from one medium into the next medium. And so when that happens, there's a refraction that happens. Or, and this is usually the case, a little bit of both is happening. Some gets reflected and some gets refracted. You may notice this if you've looked into a window. You've walked up to a door, there's a window in it, and you look in and you can see through, so you know there's light from inside the building coming toward your eye and getting all the way through, but you can also see some reflection there. We're going to treat all of the motion of light in the paths as being reversible. So if light goes in through this glass and it's going to get refracted or bent, then when it comes back, it actually follows the same path and gets bent the same way. So we'll encounter this reversibility of light as we move forward here. So first thing, when you encounter a boundary and the light returns to the same medium, then we call that reflection. I would assume that most of you, even if it's early, have probably already seen a reflection. It might not be in a mirror, but you've seen a reflection so far. So notice the wording here. It says the angle of reflection is equal to the angle of incidence, and the angles are coplanar. So here is a diagram to kind of look at what that means. So here is the reflected ray they're talking about. So we're measuring it. And this angle for the reflecting ray, I know what the reflected ray is going to be because I'm able to measure the incident ray. Notice that I don't measure from the surface. This is really important. I don't measure the angle from the surface. Instead, I create a normal 90-degree angle to the surface, and I measure those angles from the normal. Keep that in mind. Keep reminding yourself of that because that's really important when you're measuring angles. So, angle of reflection, I know where the reflection is going to be because I know what the incident angle is. They're also coplanar, which means I know that the incident ray, since it's in the plane of the screen, is going to be reflected in the plane of the screen. It's not going to come out toward me or any other way. So, law of reflection, equal angles, incident and reflected, and we are going to measure those always from the normal. So keep that foremost. If we think about the types of reflection that we see, there are two different types. One is called specular and one is called diffuse. Your book talks about reflection from a flat surface and reflection from a rough surface. And so a flat surface is going to give you a nice specular reflection. A rough surface is going to give you a diffuse reflection. Specular reflections, things like when the water is really smooth, or I can see the reflection in a whiteboard when I'm writing at the whiteboard, or a mirror that I'm using. Those are specular reflections, something that gives you a lot of light reflected back. And it's all being reflected. Remember, we're drawing the normal. So the light that comes in gets reflected out. So the incident light and the reflected light kind of stay together. If I'm looking at a diffuse reflection, this is from a rough surface. So at each point, if I draw a normal and measure those angles, and here I draw a normal and measure these angles, and then I've got a different one over here, then each one of these little pieces of the surface reflect the light just a little bit differently. And so not the incoming light and the outgoing light are not lined up in the same way. And so you can see that in the pictures with the laser. Flat gives you a nice reflection of the laser beam, but this rough one instead, it's shooting light off in all different directions because that's a nice rough surface. So when I'm looking at a mirror, I'm seeing a specular reflection, but when I'm looking at something like the keyboard on my computer, I get a diffuse reflection. So light is incident on the keyboard, it's reflected back toward me, but it's not super shiny because you can kind of feel the surface of your keyboard. It's got a little bit of roughness to it, and that diffuses the reflection so not all the light comes back exactly in the same direction.